So let's look at the probably the most important part of kinematic problem, and that is Denavit-Hartenberg notation. We call it DH notation of parameters. The idea is the following: each joint is assigned a coordinate frame, as you know. This one in red, this one in blue. Using the DH notation, you need 4 parameters to describe how a frame I relates to the previous frame I minus 1. So these DH parameters are the specifications that come to the robot dimension. Okay. If, for example, the robot is built to have, let's say, 5 revolute joints and 1 charismatic joint, then you have in the spec sheets some parameters like A and B, which are distances, and alpha and Y, which is actually meant to be theta, or these two are revolution and angular position. So if we go through from one joint to another joint, what you can see here is I have a cylinder built around the Zi minus 1 axis, and here I have another cylinder built around Zi axis, the next coordinate and the next joint. Proper rotation and translation with respect to the amount of alpha, A, D, and Y coincide. This cylinder puts it on top of their next cylinder. You see what I mean? That is the basic idea. So you can align the 2 axes just using the 4 parameters. That's the point. So what is AI minus 1? AI minus 1 is here. AI minus 1, the first DH parameter of I minus first frame or I minus first joint, is the length of the perpendicular between the joint axes. In other words, if you have 1 axis here, 1 axis there, you have 1 axis here, 1 axis here. The vertical connecting these two together is that distance is the AI minus. You see, this is vertical with respect to this and vertical with respect to this. Both of them. You see those angles are both 90 degrees. The joint axis is the axis around which the revolution takes place, which are Zi minus 1 and Zi axis, as you can see. Zi minus 1 and Zi. These 2 axes can be viewed as lines in a space. The lines in 3-dimensional space. The common perpendicular is the shortest line between the 2 axis lines, and is perpendicular to both axis lines at the same time. Okay? Do you see what this first parameter is? It is a translational value. AI1 has a millimeter or inch dimension. That's your first DH parameter. Second, we are not done yet. AI minus 1, we can look at the visual approach. It's a way to visualize the link parameter AI minus 1 is to imagine an expanding cylinder whose axis is Zi minus 1 axis when the cylinder just touches the joint axis I, the radius of the cylinder equaling to AI minus 1. So, as I said, when this cylinder aligns with this one, it has moved AI minus 1. Exactly, nothing less, nothing more. It's usually on the diagram, if the diagram already specifies the various coordinate frame, then the common perpendicular is usually the xi minus 1 axis. So, conventionally, you use this perpendicular axis as your xi minus 1 axis. It's a convention. It's nothing magic about it. And people just follow the convention. Okay? And it's like having a standard for a product, industries will follow that. Okay, and so ai minus 1 is just the displacement along the xi minus 1 to move the I minus 1 frame to the I frame. So you move this here to here. But the angle is still here because we have other parameters to worry later. We haven't rotated anything yet. We just moved ai minus 1 along the xi minus 1 axis. If the link is prismatic, then ai minus 1 is a variable, not a parameter. That's very important for you to remember. If you are looking at a Stanford arm which has a prismatic joint called in and out, okay, there is no rotation attached to it. Therefore, the DH parameter coincides with the variable itself. It's sitting on the same line between one joint and another joint. Imagine that you have this joint is connected to the other. Earlier in this slideshow, you saw a robot which goes in and out of a cavity. Okay, that is going from one joint to another joint. The length of that link is ai minus 1 coincides with that link. So you have to remember that some variables could be DH parameter, and some DH parameter could be the variable, but not all the time. A specific configuration will dictate that, the way the robot has been built. Okay, so now we got A sub I minus 1. Now what is alpha I minus 1? This is the second DH parameter. Technical definition is this: amount of rotation around the common perpendicular so that the joint axes are parallel. So remember that we move this ai minus 1. So imagine that this cylinder is aligned here. Okay. Then alpha I minus 1 is the amount of rotation which goes from here, you move it and becomes aligned here. So how much do you have to rotate around the xi minus 1 axis so that the zi minus 1 is pointing the same direction as the zi axis? So I have moved here, then I rotate to be parallel to the previous axis. Okay, that's what that's telling you. So at that point, they're both on the same direction. That is alpha I. By definition and by inspection, the second DH transformation is in radian and degrees. It's an angular position. The first one has a dimension like millimeter or centimeter or what have you. So this is the second DH parameter. The third one is another one called DI, or DI minus 1. The displacement along the zi axis needed to align ai minus 1, which is this common perpendicular, to the ai common perpendicular. You see, you have moved to the second joint, the next joint. You move physically there by some distance. Then you rotate to align it together. The distance that you have to move that point further to along the zi axis, distance of di, which is right here, di, so that it will become perpendicular to the next common normal between I and I plus 1 joint. Remember that you have a set of DH parameters, 4 for every joint. Every joint has 4 sets of parameters. We are talking about going from I minus 1 to I. But you have to remember that AI here and XI is related to a common normal from I joined to I plus 1 somewhere here beyond that. Okay. So once again, the distance along the ZI axis, needed to align AI minus 1, this AI minus 1 with AI. The common perpendicular between I and I plus 1, which is outside of the picture. Okay. In other words, displacement along the ZI to align XI minus 1 and XI axis. So, again, I repeat, you go from this point, you look at the perpendicular, you arbitrarily assign that perpendicular to be aligned with the XI minus 1 axis, and you move AI minus 1, you come here. At this point, you have reached within vicinity of your next joint, but you're not aligned. You go alpha I to align it, but you are not at the coordinates of this yet. You have to move another DI to reach the coordinate. Okay? So up to this point that I show you with this red mark, we have defined 3 DH parameters. The fourth one is theta I or yi. It's the amount of rotation around ZI axis needed to align XI minus 1 axis with the XI axis. So that is going to be yi. You rotate along the ZI axis so that XI minus 1 is aligned with XI. XI minus 1 along XI minus 1 is this. Look at the continuation of the dotted line. It rotates this much. Remember, when you go from coordinate to coordinate, you saw that in those two-dimensional examples. In order to go in a 2D area, you need both translational and rotation. They are not interchangeable. You end up in 2 different places, but they all have to come together, one after another. So basically, the DH parameters allows you to go 2 translation and 2 rotation. And those are your 4 parameters. Alpha and Y are rotational, A and D are translation. Okay? And the DH translation is going to have this kind of relationship. You have cosine of theta I, which is yi in the previous yi, again, mistypo of the author. Cosine of theta I minus sine of theta I 0 and ai minus 1. Second row is sine and cosine of theta I, alpha I minus 1, cosine of cosine and cosine combination minus sine. These are all going to come from multiplication of those different coordinates together. And the last column are going to be your coordinates of at the I minus first position. Okay. Just like the homogeneous matrix, the DH matrix is a transformation matrix from one coordinate to the next one, using a series of DH matrix manipulation and the DH parameter table. The final result is the transformation matrix from some frame to your initial frame. So eventually you can move on from Zi to Zi to I minus 1 to I plus 1, all the way to the very end. So you now have 2 competing approaches. One is the combination of translation and rotational matrices, 4 by 4. The other one is the same transformation, but within the framework of new parameters, which are consistent in terms of definition and order, which one comes first, from one joint to another joint to another joint to another. Those are DH parameters for every single joint. Okay? And as I said, they do come together in a table with your robot. And for example, when I give you a configuration of a robot, or if you go to the toolbox and print, let's say Puma 560, it gives you the homogeneous transformation, and it gives you the table, show you which of those parameters are changing, which ones are not. In a Puma robot, you have 6 coordinates, 6 angles, all 6 of them are changing, are moving. Just remember how you do it yourself. In some cases, like Adept robot. Adept robot is an offshoot of people who used to work for Unimation. After it was sold to the Westinghouse, and then Westinghouse to French, those people left the company and started their own company in California. So Adept robot, I used to own one of the robots in New Mexico, is what's called a Scala robot. It's a combination of revolute and prismatic joints. Okay, it moves like this, and then imagine that you have a robot trying to solder something on a VLSI chip. Okay, and you can go down and zap, and you can start fixing a component on a board. Okay, you have that kind of situation. In that case, some of the parameters of the robot are fixed. You cannot change it. It's dictated by the manufacturer, but some other ones are movable, variable. And that's coming with the table you can see. So now let's look at some examples of these DH parameters and the parameter table. Here's the 3 revolute joint. You have 3 rotational joints, Z0, Z1, and Z2, or I should say X0, X, Y0, and Z0, and so forth. These are the 4 DH parameters. For the first joint, the base of the robot, you have 0, 0, 0, and theta 0. That's all you have. It's just into one rotational value. Okay? Because there is no other joint before that original one to have any non-zero value. So alpha, A, and D are 0. Then you go from 0 to 1 to describe the robot with its variable and parameters. We see that going from this to this, you have an A0, this translational value. So AI minus 1 is A0, 0 for alpha, 0 for DR. Because the axis is already lined up with the previous ones, 0 and 1 are already lined up. So there is no change in, no value of alpha needed. You don't need to rotate it. When you move, you're already there. You're right up. And then you are moving along to go to this location. This is going to be minus 90 because you are going for alpha. Or you go minus 90 rotation right here. You see that rotation minus 90. A1, you go this distance to get to here. And you get D2 to be able to put you are like this, then you make it there, and then you have to move, rotate, go to the axis of Z2. So that's why now you see theta 2. Notice that in this table, some DH parameters are fixed, minus 90 degrees. I was telling you about that. Some are fixed. The rest of them are variable. So you move back and forth, you rotate here and there. That's the DH parameters. So this is a table I mentioned to you. It comes with your robot. This is just a simple example. It's nothing real about this robot example. So you have 2 uses for that. One, to describe the robot with its variable and parameters. 2 is to describe some state of the robot by having numerical values for the variable. Okay. So when you begin simulating a robot like this on the toolbox, you actually have a mechanism to find the trajectory of A1, D2, and theta 2 moving from point A to point B, or between time T0 and Tf. Okay. So again, this is the repeat of that. So going from this point to that point, end of this, you go through initial transformation of the initial condition between 0 and 1, between 1 and 2. So you have 3 homogeneous transformation matrices you multiply, or 3 DH matrices. So for all practical purpose, we are going to interchange the utility of homogeneous transformation matrix on one hand, or DH matrix on the other hand. So those are interchangeable. The good thing about it is that when you go to DH, you already know how much to move, depending on the specification of the robot. Okay. So for this particular example, you have a rotation of theta 0 along the z-axis. This is rotation along the z0 axis, the initial one. The next one, you have a translation of A0, okay, along the along the x-axis. Ended up with a translation and rotation along the z-axis and z2 axis, a d2 value. These three matrices are multiplied together to give you the DH matrix of the entire robot. Okay. So now you are leaving forward kinematics. I promise you to be a trivial problem. For some of you, it may be a bit more than trivial. But I don't want to scare you, but inverse kinematics is even worse animal than this. But don't worry, you know, your toolbox will come to your rescue. And furthermore, you can do simple homeworks, the tool-link robot, do a forward kinematics but inverse kinematics. I just want you to make sure that robotics is easy but not too easy. Okay. So here is the problem. You have one revolute joint and one prismatic joint. Here is the revolute joint here, and then it comes out of the thing, a cylinder comes out a distance like this. So this is one motion, this is another motion. You have two joints, one prismatic, one revolute. We want to find x and y coordinate of that blue point. Given x and y coordinate, what is y1 or theta 1 and what is this distance s? Okay. Look at theta, or this right here. This is the arc tangent of y divided by x, as you know. Arc tangent of y over x. That's the definition of tangent in reverse, in the reverse situation. More specifically, it could be theta is arc tangent 2 y over x, which is exactly how you do it on MATLAB. Okay. Finding s is easy because s is going to be a square root of sum of the square of the coordinates x squared plus y squared. Isn't that easy? Okay, it's very easy. You have going from here to here. It's like a right triangle. You have one angle and you have one unknown here. Okay, the right angle is obtained by the y, x, and remember x and y is given. xi1 is known. I just do arc tangent of 2 of y over x, I get theta. And and then I can take the square of the sum of the squares to give me this distance. Okay? Visualize a right triangle which has the y here and x here. Okay? This is a very simple example. Now let's look at the inverse kinematic of a two-link robot, like the double pendulum, inverted pendulum. Given L1, L2, x and y, L1 the length here, length 2 and x and y, and find y1, y2 or theta 1, theta 2. A unique solution to this problem does not exist. As you saw that already, you can have this solution or you can have this solution. Then using the givens, two solutions are possible. Sometimes, as we said, no solution is possible. Okay. For example, xy could be outside of the workspace of the robot. That robot is the wrong device for you. You have to go find another robot. So, the geometric solution is that you use the law of the cosines. Remember this from way back? No, I remember it from high school, believe it or not. Some of you may remember it from college or high school as well. The square of the third side is of ABC sides of it. Is a square plus b square times 2ab times the cosine of the angle between a and b. Okay. So in this case, you have x squared plus y squared, which is, remember, it was s here. Is equal to L1 squared plus L2 squared minus 2L1 L2 cosine of 180 minus a theta 2. That's this angle right here. 180 minus theta 2. Okay. So this side is equal to L1 squared plus L2 squared minus 2L1 L2 times the cosine of this angle, which is 180 minus theta 2. This is theta 2. This whole thing is 180 minus theta 2 is this angle. Okay? Therefore, right off the bat, we found an equation to find theta 2. The second, the revolute angle value of the second joint is actually arc cosine of x squared plus y squared minus L1 squared. These two goes on the other side. Minus L2 squared divided by 2L1 L2. Okay? And using the law of cosine, also another law of cosine, that sine of b over b is equal to sine of c over c. Then you have sine of theta 1 over L1. Sine of theta 1, which is this one, over L1. This angle right here. Sine of 180 minus theta 2, which is this angle, over this value, a square root of x squared plus s squared, which is also is equal to sine of theta 2 equal to this. So theta 1 is theta 1, is theta 1. Is theta 1 bar plus alpha. This is alpha, and this is theta 1 bar, which I showed you right here, right here. But alpha is arctangent 2 of y over x. Alpha is y over x. We know that. So theta 1 is going to be arc sine of L2 sine theta from the law of cosine plus arctangent 2 of y over x. You see that? Please take a look before you fall asleep. You have that. And I've got the indication that my time is running out. So let me see how much more do I have to worry about that. I have only 2 more slides. So let me just finish this. So the algebraic solution is that assuming that C1 is cosine of theta 1, C12 is cosine of theta 1 plus theta 2, and so forth. This is the algebraic solution of the same problem, inverse kinematic of that. Take a look at it, and if you have a question, come back, and you can find the x value, y value of of the robot, x value and y value, and then you can solve theta 1 using known x1 and x2, L1, L2, and so forth. So basically, you have to freshen up your trigonometric and mathematical treatment of triangles, okay, to solve this 2 by 2, 2-link or 1-link robots. That's all you have to do. Now, in terms of next week, if I go to the textbook, I'm going to go through this, review these 3 chapters that I have asked you to read, and please read them. Don't wait for my explanation next week. It will re-enhance your learning. We go from there, then I will go to chapter 7 and repeat what I just said this again, quickly, okay? Then I'm going to take you to velocity relationships, the Jacobian matrix, and dynamics of the robot. Okay, dynamics of the robot. And dynamics of the robot is going to have, is very, very complicated as well, unfortunately. But reading that page 26 of the second file I gave you for homework number 1 will come a long way later on to help you. And to entice you, I'll give you 25% bonus for. So you read that and put down your understanding of that Euler-Lagrange approach to dynamic modeling of the chain of mechanical joints and mechanical problems. Okay? We'll see you next week at 5:30 in the afternoon.